Hello, you who have arrived here at this unique and absolutely unrepeatable moment of existence. Take a deep breath with me for an instant. Feel the air entering your lungs, carrying with it the oxygen that was produced by plants growing under the light of our star, the sun. Where are you right now? Perhaps you're lying in your bed with soft sheets caressing your skin, while the gentle light of a lamp or the moon creates dancing patterns of shadow and brightness on the walls around you. Or maybe you're settled in a favorite armchair, one that knows perfectly the contours of your body, surrounded by the comforting silence of your home while the world outside gradually quiets for the night. What time is it where you are? Is it one of those deep, velvety nights when stars begin to emerge timidly through Earth's atmosphere, twinkling like small lighthouses of distant civilizations? Or is it that magical moment of twilight when the sun is bidding farewell to the day with its brushstrokes of gold, amber, and coral scattered across the sky like watercolor paint on an infinite canvas? Perhaps it's a lazy afternoon when light filtered through curtains creates a perfect environment for contemplation, or a serene morning when the world still guards the secrets of night in its longest shadows. How do you feel in this precious instant? Are you carrying that pleasant fatigue that comes after a day full of small discoveries and experiences? Or perhaps your mind is restless, bubbling with questions that seem to have no simple answers, thoughts that dance like leaves in the wind, refusing to settle. Maybe you're seeking that inner peace that sometimes seems as elusive as a shooting star, visible for a moment, then disappearing into the vastness. No matter what your emotional or mental state is right now, what truly matters is that you are present, conscious, alive, and that is already an extraordinary miracle in itself. Because you see, at this exact moment when you breathe, blink, think, and feel, you are participating in one of the most majestic and precise dances in the entire universe. Together, you and I are going to embark on a contemplative journey that will take us far beyond the familiar walls of your room, far beyond Earth's protective atmosphere, to the most remote reaches of the observable cosmos, where galaxies spiral in dances that last billions of years. Close your eyes for a moment and let your imagination float. Imagine that you are gently rising from where you are, passing through the ceiling, then through clouds soft as cotton, climbing higher and higher until Earth's atmosphere becomes thin and dark blue, and finally you emerge into the silent vacuum of outer space. Now you are floating in a region where there is no sound, where there is no friction, where there is no air to breathe, surrounded only by the cosmic void and by trillions upon trillions of points of light that twinkle like diamonds scattered on an infinite fabric of black velvet. Have you ever thought about this? At this exact moment, while you breathe peacefully and your heart beats in its constant and comforting rhythm, our planet Earth, this blue and green sphere we call home, is traveling through space at a speed that defies our intuitive understanding. We are moving at approximately 30 kilometers per second around the sun. To put this in perspective, this means that every second that passes, every blink of an eye, we travel a distance equivalent to 30 kilometers through the cosmic vacuum. It's as if we were on a giant, natural spacecraft, traveling through an infinite ocean of darkness dotted with light. But here is the true mystery, the fundamental question that has intrigued me for years and that I want to explore with you during this nighttime journey of contemplation. Why don't we fall into the sun? With all this dizzying speed, why aren't we simply hurled into interstellar space like passengers in a car taking a very sharp turn too quickly? Why, instead, do we remain in this elegant, precise, and apparently eternal dance, spinning around our star for billions of years in a movement that seems like perfect cosmic choreography, a ballet performed in the silent vastness of space? This is the central question that will accompany us on this contemplative journey. Why do planets remain in orbit? The answer, as we will discover together, is simultaneously elegantly simple and profoundly complex. A fascinating story of invisible forces acting on immeasurable scales, of delicate balances that remain stable for geological ages, and of mathematical harmonies that sustain not only our solar system but the entire architecture of the observable cosmos. Prepare yourself for a journey that will take us from the most fundamental physical laws to the deepest philosophical reflections about our place in the universe. From the celestial mechanics that govern planetary movement to the existential implications of our participation in this eternal cosmic dance. Imagine for a moment that you are sitting in a silent and majestic cathedral, but instead of sculpted stone walls and colored stained glass, you are surrounded by the incomprehensible immensity of outer space. What you see before you are not just distant points of light scattered randomly, but rather a grand and majestic theater where a play has been unfolding uninterruptedly for billions upon billions of years. Each star is a principal actor shining in its cosmic role, each planet a dancer executing precise and repetitive movements, each galaxy an entire theater company, and the fundamental laws of physics are the invisible musical score that governs this entire extraordinary cosmic symphony. In this cosmic theater, there are no audible applause, no curtains that open and close, no intermissions for rest. The performance is continuous, eternal, and of a beauty that transcends any work of art created by human imagination. And the most extraordinary thing of all is that we, you and I, are not just passive spectators of this cosmic performance. We are active participants, actors on the stage, dancers in the universal choreography. Have you ever wondered why, when you drop an apple from your hand, it falls inexorably toward the ground? It seems so natural, so obvious, so inevitable, that we rarely pause to question this mysterious and invisible force that keeps us firmly stuck to Earth's surface. But this same force, gravity, this fundamental and universal physical entity, is the main protagonist of our story today. It is the invisible force that keeps our coffee cup on the table in the morning, that makes rain fall from loaded clouds, that pulls tree leaves toward the ground in autumn, and that, on an incomparably larger scale, keeps planets dancing around stars in orbits that repeat with chronometric precision for geological ages. Gravity is not just a terrestrial force limited to our small blue planet. It is truly universal, cosmic, fundamental. Every object in the entire universe, from the smallest particle of cosmic dust floating in interstellar vacuum to the largest spiral galaxies containing hundreds of billions of stars, exerts a gravitational attraction on all other objects, no matter how distant they may be. It's as if each particle of the cosmos were constantly whispering to all other particles in a universal language. Come here, come closer, feel my presence. Imagine this for a moment. At this exact instant, while you are there comfortably positioned, you are exerting a tiny but real and measurable gravitational force on the moon that orbits our planet. And the moon, in turn, is exerting a gravitational force on you. It's a force imperceptible to your senses, completely undetectable by your conscious experience, but it exists, it is real, it can be measured by sufficiently sensitive instruments. You and the moon are gravitationally connected across 384,400 kilometers of empty space. But here is where the story becomes really fascinating and where the mystery begins to reveal itself. If gravity is always, constantly, inexorably pulling everything closer to everything else, why doesn't the entire universe simply collapse into one large compact ball of matter? Why aren't stars simply sucked into each other? Why aren't planets invariably pulled into the stars they orbit? Why does this apparent stability exist? This persistence of structures and patterns that maintain themselves for billions of years? The answer lies in another fundamental property of matter and motion: inertia. Newton, that extraordinary English scientist who lived more than 3 centuries ago and whose genius still amazes us, had one of the most profound and revolutionary insights in the history of human thought. He realized that an object in motion tends to continue in motion, in a straight line at constant velocity, unless some external force acts upon it to alter that motion. This is inertia, the tendency of matter to resist changes in its state of motion. You can feel this viscerally when you're in a car that brakes suddenly in an emergency. Your body wants to continue moving forward at the same speed the car was traveling, even though the car has stopped abruptly. Your bodily inertia resists the sudden change in motion. It's this same physical property that, on a cosmic scale, prevents the universe from simply collapsing under its own gravity. Now imagine combining these two fundamental forces, gravity constantly pulling everything toward the center, trying to bring all objects closer, and inertia constantly trying to keep everything in uniform rectilinear motion, resisting any change in direction or speed. What happens when these two titanic forces meet and interact in perfect dynamic equilibrium? Something truly magical, beautiful, and stable emerges: the orbit. An orbit is essentially an elegant compromise between these two opposing tendencies. It's as if nature had found a diplomatic solution to a conflict of forces, a way to satisfy both demands simultaneously. Gravity manages to pull the object, but cannot bring it closer. Inertia manages to keep the object in motion, but cannot take it away in a straight line. The result is a circular or elliptical movement that can persist, theoretically, forever. Let's do a deep imagination exercise together. You and I visualize yourself at the top of an extraordinarily high mountain, so high that it transcends even Mount Everest. A hypothetical mountain that rises so far above Earth's surface that you can literally see the majestic curvature of our blue planet extending like a gentle arc on the distant horizon. The air here is rarefied, almost non-existent, and the sky above has a dark blue tonality that approaches the black of outer space. You have in your hands an ordinary stone, perhaps a pebble you collected on the climb up the mountain, something simple and tangible. Now you decide to conduct a mental experiment that will reveal one of the most profound truths about the nature of planetary motion. You throw this stone horizontally, parallel to the curved surface of Earth extending below. What happens? The stone flies through the air for a few meters, tracing a graceful parabola, and then falls inexorably to the ground. Pulled by Earth's gravitational attraction, gravity won, as it always does in our everyday experience. Now imagine that you can throw this same stone with more force, with more energy. It flies farther before succumbing to gravity and falling. Even more force, and it flies even farther, tracing a larger arc through the sky before finally touching the ground. But here is the truly revolutionary thought. The idea that changed our fundamental understanding of celestial mechanics. If you could throw this stone with sufficient force, if you could impart sufficient horizontal velocity to it, it would fly so far that when it finally began to fall due to Earth's gravitational attraction, the ground itself would have curved away from it due to the planet's sphericity. Think about this carefully. Earth is round, not flat. This means that Earth's surface is constantly falling away from any straight line you can draw tangent to it. If the stone flew fast enough horizontally, it would constantly be falling toward Earth, but Earth would constantly be curving away from the stone's trajectory. The stone would continue falling, faithfully obeying the law of gravity, but would never touch the ground, because the ground would always be a little farther, always a little below the stone's trajectory. This, my contemplative friend, is precisely what an orbit is. An orbit is not a state of absence of gravity, as many people incorrectly imagine. An orbit is a state of perpetual free fall. A planet orbiting the sun is actually constantly falling toward the sun, obeying the laws of gravity exactly like the apple falling from the tree. The crucial difference is that the planet falls in such a way that it never reaches the sun, because its lateral velocity is exactly correct for it to continue missing the target eternally. It's as if each planet were an extraordinarily skilled cosmic tightrope walker, walking on an invisible tightrope stretched through the vacuum of space, balancing precisely between two titanic and opposing forces, the star's gravity that pulls it inexorably inward, trying to bring it closer, and the tangential velocity that constantly pushes it outward, trying to hurl it away into the immensity of interstellar space. Think about our own Earth, this blue and green planet we call home. Our world is traveling through the vacuum of space at a velocity of approximately 30 kilometers per second in its orbit around the sun. This velocity is not accidental, not arbitrary, not a cosmic coincidence. It is exactly, precisely, mathematically the velocity necessary for the centrifugal force, the tendency to be hurled outward due to circular motion. Like the sensation you have when a car takes a sharp curve to perfectly balance the sun's gravitational attraction. If Earth were traveling just a little slower in its orbit, even just a few kilometers per second slower, solar gravity would gradually win, and our planet would begin a slow and inexorable spiral toward the sun. If we were traveling a little faster, just a few kilometers per second faster, we would completely escape the sun's gravitational attraction and be hurled into interstellar space, condemned to wander eternally through the cold darkness between stars. It's a delicate dance, a symphony of forces in perfect and dynamic equilibrium. And the most impressive and wonderful thing is that this dance is not unique to Earth, not an isolated or special phenomenon. Every planet in our solar system, every moon that orbits every planet, every asteroid and comet, all execute their own versions of this fundamental cosmic choreography. Mercury, the planet closest to the Sun, small and rocky like a dark pearl, dances in a frantic and accelerated rhythm, completing a complete orbit in just 88 Earth days. Its proximity to our star means it needs to move very quickly to avoid being pulled into it. Venus, wrapped in its thick and mysterious clouds, executes a slightly slower waltz, taking 225 Earth days to complete its orbital journey. Earth, our home, dances to the rhythm we know so well, 365 days for a complete turn, defining our year and our seasons. Mars, the red planet that has fascinated human imagination for millennia, executes a slower and more contemplative dance, taking almost 2 Earth years to complete an orbit. And in the outer regions of the solar system, the gas giants execute even more majestic and slow movements. Jupiter, the king of planets, takes almost 12 Earth years for a complete orbit. Saturn, with its dazzling rings, dances for 29 years. Uranus, tilted sideways in a unique posture, takes 84 years. And Neptune, the most distant of the major planets, executes the slowest and most majestic of planetary waltzes, taking an impressive 165 Earth years to complete a single turn around the Sun. Have you ever wondered what maintains this extraordinary precision? Why doesn't this cosmic dance unravel over the millennia? Why don't planets gradually decelerate and spiral into the Sun or accelerate and escape into space? The answer lies in the very nature of the space vacuum. In space, there is no atmosphere, no friction, no resistance of any kind to decrease planetary velocities or disturb their orbits. Once in motion, according to Newton's first law, they continue moving forever, trapped in the gravitational dance with their star, executing their eternal orbital choreography without ever getting tired, without ever slowing the rhythm, without ever losing step with the cosmic music that governs them. There's something profoundly poetic and almost mystical in the idea that the entire universe, in all its incomprehensible vastness and astonishing complexity, is governed by invisible laws, by elegant mathematical patterns that repeat with perfection from the smallest subatomic particles to the largest cosmic structures we can observe. Imagine that you are in an infinite cosmic library, where each book contains one of these fundamental laws of nature, where each page reveals an aspect of the mathematical harmony that sustains all physical reality. One of the most important volumes in this imaginary library would be dedicated entirely to Kepler's 3 laws. 3 elegant and profoundly revealing principles that describe with exact mathematical precision how planets move in their celestial orbits. These laws were discovered by Johannes Kepler, an extraordinary German astronomer who lived between the 16th and 17th centuries, a time when humanity was just beginning to understand that Earth was not the center of the universe. Kepler spent years of meticulous work, careful observations, laborious calculations done by hand, studying the movement of planets, especially Mars, which had an orbit particularly difficult to explain using the astronomical theories of the time. He had access to the most precise observational data available at the time, collected by his mentor Tycho Brahe, and was determined to find the mathematical pattern that would explain these celestial movements. What Kepler discovered revolutionized our understanding of the cosmos. He discovered that planetary orbits are not perfect circles, as had been thought since the time of the ancient Greeks. Instead, they are ellipses, delicate and elegant oval shapes, like circles that have been gently compressed or elongated. Imagine a perfect circle and then imagine someone gently pressing it between their fingers, deforming it slightly to create an oval shape. This discovery was truly revolutionary because it destroyed the notion that the cosmos should be geometrically perfect, revealing instead that the universe is beautiful precisely in its mathematical imperfection. Kepler's first law tells us that planets orbit the Sun in ellipses, with the Sun occupying one of the foci of the ellipse. To understand what this means, imagine an ellipse drawn on a sheet of paper. An ellipse has 2 special points called foci. If you place two nails on a table, stretch a string around both nails, and then use a pencil to stretch the string and draw a curve, you will create a perfect ellipse. The 2 points where the nails are located are the foci of the ellipse. In the case of a planetary orbit, the Sun is located at one of the foci of the orbital ellipse, not at the center. This means that sometimes a planet is closer to the Sun and sometimes it is more distant. When Earth is closest to the Sun, which happens in early January, we call this position perihelion. When it is most distant, which happens in early July, we call it aphelion. It's an interesting irony to note that winter in the northern hemisphere happens when we are closest to the Sun, demonstrating that Earth's distance from the Sun is not the main factor determining seasons. Seasons are caused primarily by the tilt of Earth's axis, not by orbital distance variation. Kepler's second law is even more fascinating and reveals something profound about the nature of planetary motion. It tells us that a planet moves faster when it is closer to the Sun and slower when it is more distant. It's as if the Sun were the conductor of a cosmic orchestra, accelerating and decelerating the rhythm of the music according to the proximity of each planetary musician. To visualize this, imagine a figure skater on ice executing a spin. When the skater pulls their arms close to their body, they spin faster. When they extend their arms away from their body, the rotation slows down. Planets do something similar in their elliptical orbits, but instead of using arms, they use their variable distance from the Sun to naturally accelerate and decelerate. Mathematically, Kepler's second law states that an imaginary line connecting a planet to the Sun sweeps equal areas and equal times. This means that when a planet is closer to the Sun and moving rapidly, it sweeps a small but wide area. When it is more distant and moving slowly, it sweeps a large but narrow area. The two areas are always equal for equal time intervals. Kepler's third law is perhaps the most mathematically elegant and reveals a profound cosmic harmony. It establishes a precise and invariable relationship between the time a planet takes to complete an orbit, its year, and its average distance from the Sun. More distant planets not only move slower due to weaker solar gravity at greater distances, but also have much larger orbits to traverse, so they take much more time to complete a full turn. The relationship is mathematically exact. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. In other words, if you take the time a planet takes to orbit the Sun, square that number, and divide by the planet's average distance from the Sun cubed, you will get the same number for all planets in the solar system. It's a perfect mathematical harmony, as if the universe were a musical composition where each note has its exact and precise position in the cosmic score. This mathematical relationship means we can predict with absolute precision where any planet will be at any future moment, as long as we know its current position and velocity. It's this mathematical predictability that allows astronomers to calculate eclipses centuries in advance, program space missions to encounter distant planets at specific moments, and understand the mechanics of planetary systems around other stars. But have you ever wondered deeply why these laws work? Why does the universe obey such precise and elegant mathematical patterns? Why does nature seem to have a preference for mathematical harmony? The answer came decades after Kepler's time, with the work of Isaac Newton, who showed that Kepler's laws were natural and inevitable consequences of even more fundamental principles, the universal laws of gravitation and motion. Newton realized that Kepler's laws were not just empirical descriptions of how planets move, but were manifestations of fundamental physical principles that govern all matter and energy in the universe. Gravity and inertia, working together according to precise mathematical laws, automatically produce elliptical orbits, orbital velocity variations, and the harmonic relationship between period and distance that Kepler had discovered observationally. Close your eyes for a moment and allow your imagination to transcend the limits of common sensory experience. Imagine that you have the extraordinary and almost supernatural ability to feel gravity not as an abstract physical force, but as a true language, as a universal means of communication that permeates the entire cosmos. In this gravitational language, every mass in the entire universe would be constantly whispering to all other masses, creating a continuous cosmic conversation, a universal dialogue that never stops, never rests, never falls silent. The Sun, with its gigantic and incomprehensible mass, approximately 333,000 times Earth's mass, so large that it could contain more than 1 million planets the size of ours, is constantly speaking gravitationally with all planets, asteroids, comets, and dust particles throughout the solar system, saying in a voice that is simultaneously gentle and irresistible, "Come here, feel my attraction, let me embrace you with my gravity." And each planet responds in its own gravitational voice. "I feel your attraction. Sun, I feel your powerful presence, but I am also moving, I also have my own inertia, so I will dance around you. I will orbit in your vicinity, but I will not fall into you." Gravity is truly universal. It is the only force we know that works exactly the same way in all places of the observable cosmos, from laboratories on Earth to the most distant galaxies our telescopes can detect. The force that makes an apple fall gracefully from the tree in your backyard is precisely the same force, operating according to the same exact mathematical laws, that keeps the moon orbiting Earth in its monthly dance, that keeps Earth orbiting the Sun in its annual journey, that keeps the entire solar system orbiting the massive center of the Milky Way in a journey that takes approximately 230 million years to complete. It's a language that all objects in the universe understand instinctively, automatically, without need for learning or translation. From the smallest particle of cosmic dust to the largest elliptical galaxy containing trillions of stars, everything in the universe speaks gravitation fluently. Newton formulated this universal language in precise and elegant mathematical terms. The gravitational force between any two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This may sound like an abstract and lifeless formula, but it is actually one of the most beautiful and powerful descriptions of nature ever, discovered by the human mind. Let's make this law more tangible and visualizable. Imagine that you have two powerful magnets in your hands. When you bring them close, the magnetic force between them increases dramatically. When you move them apart, the force weakens rapidly. And the larger and more powerful the magnets, the stronger the attraction between them. Gravity works in a very similar way, but instead of magnetism, it's the mass itself, the quantity of matter in an object, that creates the attraction. If you double an object's mass, you double its gravitational attraction. If you double the distance between two objects, you reduce the gravitational force between them by a factor of 4. If you triple the distance, the force becomes 9 times weaker. This inverse square relationship means that gravity decreases very rapidly with distance, but never completely disappears. But here is something truly fascinating, and that may leave you amazed. Gravity is not just a force that pulls objects toward each other. Einstein showed us in his theory of general relativity, one of the most extraordinary intellectual achievements in human history, that gravity is actually a curvature of the very fabric of space-time. This is an idea so profound and revolutionary that even today, more than a century after Einstein proposed it, it continues to challenge our intuition and expand our understanding of reality. To visualize this revolutionary idea, imagine a large elastic bed stretched horizontally. If you place a heavy bowling ball in the center of the bed, it will create a deep and curved depression in the elastic fabric. Now, if you roll a ping-pong ball along the edge of the bed, it will not follow a straight line. Instead, it will be naturally attracted to the depression created by the bowling ball, following the curves of the deformed fabric. This is similar to what happens in real space-time. Massive objects like the Sun curve the fabric of space-time around them, creating gravitational depressions, and other smaller objects like planets follow these curvatures naturally. What we perceive as the force of gravity is actually just objects following the most natural path through curved space-time. Have you ever thought that, at this exact moment, while you are there comfortably positioned, you are feeling the gravitational effects of objects that are trillions upon trillions of kilometers away? The force is tiny, completely imperceptible to your senses, but it exists, it is real, it can be measured. You are gravitationally connected to all the stars you can see in the night sky, to all the distant galaxies whose photons took billions of years to reach your eyes, to all the planets orbiting other stars in remote solar systems. There is an invisible but real web of gravitational forces connecting literally everything in the observable universe. Every atom in your body is exerting a tiny gravitational attraction on every atom in every visible star in the night sky. You are in a gravitational dance with the entire cosmos. And this cosmic web of gravity is precisely what allows the orbital dance to continue for billions of years with such stability and precision. Every planet is trapped in this complex gravitational web, following the curved paths of spacetime created by stars and other massive objects. It's as if each solar system were a three-dimensional work of art sculpted in the very fundamental structure of space and time. Gravity also acts on much larger scales than individual planetary systems. It keeps stars grouped in galaxies, galaxies grouped in clusters, and galaxy clusters organized in a large-scale cosmic structure that astronomers call the cosmic web, a gigantic three-dimensional network of dark matter filaments and galaxies, extending for billions of light years in all directions. Even the expansion of the universe, discovered by Edwin Hubble in the early 20th century, is a continuous battle between gravity trying to pull everything together and dark energy trying to accelerate cosmic expansion. It's literally a titanic struggle on a universal scale, with the final fate of the cosmos depending on which force eventually prevails. There is something that can be described only as truly miraculous in the extraordinary stability of planetary systems. When you stop to consider all the variables involved, all the forces that could disturb orbits, all the possibilities for instability and chaos, it becomes almost incomprehensible that planets can maintain stable orbits for billions of years. Think about this with the depth it deserves, approximately 6 billion years ago. When Earth formed from the gradual coalescence of dust and debris in the protoplanetary disk that circled the young sun, our planet somehow found exactly the right velocity and exactly the right distance to establish and maintain an extraordinarily stable orbit. Earth did not end up too close to the sun, which would have transformed it into a scorching and uninhabitable desert like Venus, where surface temperatures are hot enough to melt lead and where a dense carbon dioxide atmosphere creates a runaway greenhouse effect. Nor did it end up too far away, which would have condemned it to be a cold and sterile world like Mars, where the rarefied atmosphere and greater distance from the sun resulted in a planet where liquid water cannot exist stably on the surface. Instead, Earth found that special and extraordinarily narrow zone that astronomers poetically call the habitable zone or Goldilocks zone, neither too hot nor too cold, but exactly right to allow water to exist in all three states, solid, liquid, and gas, and for complex life to emerge, evolve, and flourish for billions of years. But have you ever wondered deeply what maintains this remarkable stability? Why doesn't the solar system gradually become disorganized over the eons? Why don't planetary orbits slowly decay or become unstable? The answer lies in a fascinating phenomenon that scientists call orbital resonance, a kind of subtle and complex cosmic music where planets gravitationally influence each other in ways that maintain the entire system in dynamic equilibrium. Imagine a symphony orchestra where each musician not only plays their own individual score, but also listens attentively to all other instruments and constantly adjusts their rhythm, tuning, and dynamics to maintain the general harmony of the music. Planets do something extraordinarily similar in their mutual gravitational interactions. They are constantly listening to each other gravitationally and making subtle adjustments in their orbits to maintain system-wide stability. Jupiter, the gas giant that is larger than all other planets in the solar system combined, acts as a kind of gravitational conductor. Its enormous mass, more than 300 times Earth's mass, gives it a disproportionate gravitational influence over the entire solar system. Jupiter uses this influence to keep smaller planets in their correct orbits, but its importance goes far beyond that. If it weren't for Jupiter's presence in its current orbit, many asteroids and comets from the outer solar system would constantly bombard the inner planets. Including Earth, Jupiter acts as a kind of cosmic vacuum cleaner, using its powerful gravity to capture or deflect potentially dangerous objects that could collide with Earth and cause mass extinctions like the one that eliminated the dinosaurs 66 million years ago. Jupiter's protective influence is so important that some astronomers speculate that complex life may be rare in the universe precisely because most planetary systems don't have a well-positioned Jupiter to protect their inner planets from constant bombardment. It's as if Jupiter were a giant protective shield, a silent guardian that allows the delicate dance of life to continue here on Earth without constant catastrophic interruptions. But Jupiter's protection is not just about capturing asteroids and comets. Its presence also helps stabilize the orbits of other planets through complex gravitational resonances. Many planets and moons in the solar system are in orbital resonance with each other, which means their orbital periods are in simple and elegant mathematical proportions. For example, Neptune completes exactly 2 orbits in the time Pluto completes 3. This 2-2-3 resonance is not a cosmic coincidence. It's the result of billions of years of gravitational interactions that gradually tuned these objects' orbits until they found a stable and harmonious configuration. Jupiter's moons offer even more dramatic examples of orbital resonance. Io, Europa, and Ganymede, 3 of Jupiter's 4 large Galilean moons, are in a triple resonance where Io completes 4 orbits in the time Europa completes 2 and Ganymede completes 1. This synchronization not only keeps the orbit stable, but also heats Io's interior through variable tidal forces, creating the most spectacular active volcanoes in the solar system. What if the universe were slightly different? What if gravity were just a little stronger or a little weaker? What if planets had formed with slightly different masses, or if Jupiter had formed in a different orbit? Any small change in these fundamental conditions could have resulted in a completely different solar system, perhaps one where life never had the opportunity to arise and develop. Computer simulations show that planetary systems are surprisingly sensitive to initial conditions. Small changes in the mass or position of giant planets can result in completely chaotic systems where planets are ejected from the system or collide with each other. The fact that our solar system has maintained stability for billions of years suggests that we found a particularly special and improbable configuration. This leads us to a profound and humbling reflection. We are here, conscious and capable of contemplating the cosmos, because the universe found an extraordinarily delicate balance between order and chaos, between forces that could create and forces that could destroy. Our existence is, in itself, living proof that this perfect balance is possible and mysteriously natural. There is an almost spiritual dimension to this realization. We are direct products of Earth's orbital stability, but we are also conscious witnesses to this stability. We are simultaneously participants in the cosmic dance and unique observers capable of understanding and appreciating its mathematical beauty. It's as if the universe had developed the capacity to contemplate itself through our consciousness. Let's take a deep and contemplative pause to reflect on something that is truly extraordinary and that may be one of the most dizzying realizations the human mind can achieve. At this exact moment, while you are there, perhaps feeling the comforting tranquility of night settling around you, perhaps hearing the gentle silence that marks the transition between day and night, you are actively participating in a symphony of movement that is absolutely vertiginous in its magnitude and precision. Think with me about the multiple layers of motion of which you are an unconscious but active participant. First, Earth is rotating around its own axis like a giant top, completing a full rotation every 24 hours. At the equator, this means you are moving at approximately 1,670 kilometers per hour due to Earth's rotation alone. If you live at higher latitudes, your linear velocity due to rotation is somewhat less, but still impressive. Simultaneously, while Earth spins like a top, our entire planet is orbiting the Sun at a velocity of approximately 108,000 kilometers per hour. To put this in more visceral perspective, every second that passes while you blink, breathe, or have a thought, you and the entire planet Earth travel about 30 kilometers through the vacuum of outer space. But the symphony of motion doesn't stop there. The entire solar system, the Sun, all planets, all moons, all asteroids and comets, is moving as a unit through our galaxy, the Milky Way, at a velocity of approximately 720,000 kilometers per hour. We are on an epic journey around the galactic center that takes about 230 million years to complete. This means that since complex multicellular life arose on Earth, our solar system has completed only a few orbits around the center of the galaxy. And there are still more layers in this cosmic symphony of movement. The Milky Way itself is moving through local space, gravitationally attracted toward the Great Attractor, a massive concentration of matter situated hundreds of millions of light years away. And the entire observable universe is expanding, with distant galaxies moving away from us at velocities approaching the speed of light. Do you feel all this dizzying velocity? Of course not, and this is part of the deep and almost mystical magic of physics. You don't feel it because you are moving harmoniously along with everything around you. It's exactly like being inside a train that travels smoothly along the tracks. You only notice the movement when you look out the window and see the landscape passing by. In our cosmic case, the window consists of distant stars, which appear fixed and immutable in the night sky when we look at them on a single night, but which are actually all participating in their own complex cosmic dances, all moving through the galaxy on trajectories that extend over millions and billions of years. This absence of sensation of movement reveals something profound and philosophical about the very nature of physical reality. Movement is fundamentally relative. There is no fixed and absolute reference point in the universe from which we can measure absolute velocity. Everything is in motion relative to everything else. It's as if the universe were a gigantic cosmic dance where there is no fixed stage. The dancers themselves are the stage, and the stage is constantly moving and evolving. Einstein formalized this profound intuition in his theory of special and general relativity, showing that there is no privileged reference frame in the universe. There is no special place where you can stop and say, "Here, finally, I am truly at rest." Everything is relative, everything is in motion in relation to everything else. But here is something that may leave you even more amazed and contemplative. All this extraordinary cosmic movement requires no continuous energy to be maintained. Once an object is in motion in the vacuum of outer space, where there is no atmosphere, no friction, no resistance of any kind, it will continue moving forever according to Newton's first law, the law of inertia. This is fundamentally different from our everyday experience here on Earth's surface, where air friction, wheel friction on pavements, water resistance always gradually slow down any moving object. Here on Earth, to keep something in constant motion, we need to continuously apply energy to overcome these resistance forces. But in space, once in motion, objects simply continue moving indefinitely. It's as if the universe were a perfect and natural perpetual motion machine. Of course, perpetual is a relative term even on cosmic scales. Eventually, in trillions of years in the distant future, stars will run out of nuclear fuel and begin to die. The accelerated expansion of the universe may separate galaxies beyond any possibility of gravitational interaction. And the second law of thermodynamics may lead the cosmos to a state of maximum entropy. But for now, for billions upon billions of years yet to come, this extraordinary cosmic dance will continue with its chronometric precision, its mathematical beauty, its physical harmony. It's a dance that transcends any choreography created by human imagination in its complexity, elegance, and temporal scale. There is a profound poetic beauty in this idea of cosmic perpetual motion. Each planet is like a dancer who never gets tired, never needs to stop to rest, never loses the rhythm of cosmic music. Each planet executes the same fundamental orbital choreography repeatedly, but each repetition brings its own subtle variations, its own nuances, its own thematic developments. Earth doesn't follow exactly the same spatial trajectory each year that passes. There are small variations caused by the gravitational influence of other planets, especially Jupiter and Saturn, by the slightly variable shape of our elliptical orbit, by minuscule perturbations from distant asteroids, by the slow precession of Earth's axis, and by dozens of other subtle factors. These minuscule orbital variations, accumulated over tens of thousands of years, are responsible for Earth's long-term climate cycles, including ice ages and interglacial periods. It's extraordinary to realize that orbital variations almost imperceptible on human timescales can have dramatic effects on global climate on geological timescales. Have you ever wondered deeply why? Why did the universe choose to be a place where movement is natural and fundamental, where absolute rest is impossible? Why does the very structure of physical reality favor dynamics over statics? Perhaps it's because movement is absolutely fundamental to the very existence of life, complexity, evolution, beauty. A truly static universe would be a dead universe, without change, without development, without possibility of growth or evolution. It's movement that brings change, and it's change that makes possible biological evolution, the growth of complexity, the creation of new forms of organization and beauty. Perhaps the universe's perpetual motion is the necessary condition for consciousness, to emerge and contemplate its own existence. Now, let's expand our contemplation far beyond the familiar boundaries of our solar system, into the unimaginable depths of interstellar space, where trillions upon trillions of planets execute their own unique versions of the fundamental orbital dance around stars that are, simultaneously, similar to our Sun in their fundamental physical properties, but also dramatically different in their specific details. Did you know that there are an estimated trillions of planets just in our galaxy, the Milky Way? And that each of these distant worlds is executing its own personalized version of orbital choreography, following the same fundamental physical laws that govern our solar system, but creating infinite variations on the basic theme of gravitational dance between planets and stars. Some of these exotic worlds orbit stars very different from our Sun. There are planets that dance around red giants, old and swollen stars that have expanded far beyond their original size, creating orbital conditions that have no parallel in our solar system. Others orbit white dwarfs, dense and hot remnants of stars that have already exhausted their nuclear fuel and collapsed to approximately Earth size while maintaining a mass similar to the Sun's. Perhaps even more fascinating are planets that orbit binary stars, systems where two stars dance around each other in an intimate gravitational waltz, while planets execute extraordinarily complex orbital choreographies around both stars or around just one of them. Imagine for a moment what it would be like to live on a planet orbiting a binary star system. What kind of sky would this world have? During certain epochs of the planetary year, two stars would be simultaneously visible during the day, creating two distinct shadows for each object on the planet's surface, producing patterns of light and shadow that would be completely alien to our terrestrial experience. During other epochs, one star would set on the horizon while the other remained high in the sky, creating prolonged periods of perpetual twilight where the planet would never experience true darkness nor full daylight. And such a planet's orbit would be much more complex and intricate than any orbit in our solar system. Instead of following a relatively simple ellipse around a single star, a planet in a circumbinary orbit would trace intricate three-dimensional patterns around the binary system's center of mass, patterns that might appear chaotic to short-term observation, but that actually follow precise and deterministic dynamical laws when viewed on sufficiently long timescales. Exoplanet discoveries in the last 3 decades have revealed a diversity of worlds that challenges and expands our imagination. There are planets that complete an entire orbit around their star in just 16 Earth hours, worlds where a year is shorter than a day on Earth. In these ultra-fast orbit worlds, the star's gravitational force is so intense, and the orbital velocity so extreme that the planetary atmosphere itself may be constantly being stripped away and lost to space. At the opposite extreme, there are planets with orbits so elliptical and elongated that sometimes they are closer to their stars than Mercury is to the Sun. Sometimes more distant than Mars is from the Sun. Imagine the extreme temperature variations these worlds must experience during the course of their elongated years. During perihelion, the point of closest approach to the star, the planetary surface might be hot enough to vaporize metals. During aphelion, the point of greatest distance, the entire atmosphere might freeze and fall like snow. There are planets that orbit their stars so closely that one face is permanently turned toward the star due to tidal locking, while the other face is in eternal night. These tidally locked worlds would have hemispheres of absolute climatic extremes, one side blazingly hot where rocks might be in liquid state, another side frozen where even the atmosphere might freeze into solid deposits. Between these two extremes, there would be a zone of perpetual twilight where, perhaps more moderate conditions could allow the existence of liquid water and possibly life. Have you ever thought deeply about what it would be like to experience life on a world with a dramatically different orbit from Earth's? Consider a hypothetical planet with a year of 1,000 Earth days. Seasons on this world would last hundreds of Earth days each. If plants existed there, they would have to develop survival strategies completely different from terrestrial plants. Perhaps they would develop the ability to hibernate for months at a time during extraordinarily long winters. Or perhaps they would migrate. Yes, plants that migrate, following appropriate temperature belts as they move slowly across the planet during extended seasons. Hypothetical animals on such a world could evolve life cycles synchronized with these prolonged seasons, perhaps hibernating for half their lives, or migrating across entire continents following the slow but inexorable seasonal changes. Intelligent civilizations that evolved on such worlds would have completely different concepts of time, planning, and natural cycles. But perhaps the most fascinating thing of all is to realize that, regardless of how exotic, strange, or alien a planetary orbit might be, the same fundamental physical laws apply universally. Gravity, inertia, the dynamic balance between centripetal and centrifugal forces, all of this works exactly the same way, whether on a planet orbiting a red dwarf star hundreds of light years from here or here on Earth. It's as if the universe uses the same fundamental musical language in all its regions, but creates infinite variations, creative improvisations, unique thematic developments on the same basic gravitational melody. Each planetary system is an original interpretation of the same fundamental cosmic composition. And this discovery that so many different worlds exist, each with its own unique and personalized orbital dance, makes us realize something simultaneously humbling and inspiring about our own situation here on Earth. On one hand, we realize that our situation is not unique. We orbit our star following the same physical laws that govern trillions of other worlds. On the other hand, we realize that the specific conditions of our orbit, our precise distance from the Sun, our specific orbital velocity, Jupiter's protective mass, the long-term stability of the entire solar system, created extraordinarily special conditions that allowed complex life not only to arise, but to flourish and evolve for billions of years until giving rise to consciousness, capable of contemplating its own cosmic existence. There is an ancient and profoundly poetic idea that goes back to the Greek philosophers of antiquity, an idea called music of the spheres or harmony of the spheres. Ancient thinkers, including Pythagoras and his followers, believed that the movement of planets through the heavens created a musical harmony inaudible to ordinary human ears, but perceptible to the soul in states of deep contemplation and spiritual elevation. Although today we know that sound cannot travel through the vacuum of outer space, since sound waves require a material medium to propagate, and the space between planets is essentially empty. There is a profound and metaphorical truth in this ancient idea that modern science has revealed in ways that Greek philosophers could never have imagined. Planets really do create a kind of cosmic music, but it's a music composed of gravitational frequencies, harmonious orbital periodicities, resonances that extend over millions of kilometers and remain stable for millions of years. When two or more planets are in orbital resonance, a situation where their orbital periods are in simple mathematical proportions, like 2 to 1 or 3 to 2, they create patterns that repeat regularly, like musical chords sustained through centuries and millennia. To better visualize this cosmic music, imagine if we could dramatically speed up time and watch planetary movements as if they were an accelerated symphony. Jupiter, with its majestic orbital period of 12 Earth years, would be like a deep and profound note, a continuous and solemn bass that sustains the entire cosmic melody with its massive and stabilizing presence. Mercury, completing 4 rapid orbits for each Earth year, would be like a bright and sharp note, a cosmic piccolo dancing quickly around the Sun. Earth, with its 1-year orbit that defines our most fundamental temporal unit, would be like a middle and constant note, a reference tone to which all other harmonies relate. Mars, with its 2 Earth years per orbit, would create a harmony in the octave below Earth. Venus, with its 0.6 Earth years per orbit, would add a bright harmonic fifth to the composition. But this cosmic music is not just a poetic metaphor. Astronomers have discovered that many planetary systems, both in our solar system and around other stars, exhibit resonance patterns that are mathematically identical to the harmonic proportions found in terrestrial music. There is an extraordinary exoplanetary system called TRAPPIST-1, located approximately 40 light-years from Earth, which contains 7 Earth-sized planets orbiting a small red dwarf star. What makes this system truly remarkable is that the orbital periods of these 7 planets are in almost perfect resonances with each other, creating a chain of orbital harmony that is precisely analogous to a complex musical chord. If you could speed up time and hear these orbital resonances as sound frequencies, they would sound like a rich and complex but perfectly harmonious musical chord. The planets of TRAPPIST-1 are literally singing a mathematical song as they dance around their star. Have you ever wondered deeply why the universe naturally tends to create these harmonic patterns? Why do planets gravitationally organize themselves into resonances? The answer lies in the very nature of physical and mathematical stability. Systems that are in harmonic resonance are intrinsically more stable over time than systems with random or discordant periodicities. It's as if the universe prefers harmonious configurations because they last longer, because they are less prone to destructive perturbations, because they represent more elegant equilibrium solutions to the complex equations of celestial mechanics. Orbital resonances are, in essence, the way nature has found to solve the many-body problem in gravitational interaction, a problem so mathematically complex that it has no exact analytical solutions for more than 2 bodies. This leads us to a deep philosophical reflection on the fundamental nature of beauty and harmony. Why do human beings find music based on simple mathematical proportions beautiful? Why do certain numerical relationships seem naturally harmonious to us while others seem discordant? Perhaps it's because we are literally made of the same matter that executes this harmonic cosmic dance. Every atom in your body was forged in the nuclear heart of a star that once executed its own orbital dance around the center of the galaxy. The calcium that forms the structure of your bones, the iron that carries oxygen in your blood, the carbon that forms the complex organic molecules of your DNA, all these elements were created by nuclear fusion processes in stars that lived and died billions of years before the formation of the solar system. When Carl Sagan poetically said that we are made of star stuff, he was being literally precise, not just metaphorical. You are literally constituted of matter that participated in the cosmic dance for billions of years, before organizing itself into the complex form that is your conscious body. Perhaps this is why the music of the spheres resonates so deeply in our soul, because we are an integral part of the very symphony we are trying to understand. What if we could really hear this cosmic music in all its complexity? What if we could perceive gravitational resonances as we perceive sound waves? What if we could tune our consciousness to the orbital frequencies of planets? Perhaps we would discover that we are constantly immersed in a symphony of incomparable beauty, a music that connects the smallest atom to the largest galactic structures in a continuous universal harmony. There is evidence that this cosmic music may have subtle but real influences on terrestrial phenomena. The very existence of ocean tides is a direct manifestation of the gravitational music of the Earth-Moon system. Tides follow precise mathematical rhythms that reflect the relative orbital positions of Earth, Moon, and Sun. It's as if the oceans were dancing to the sound of the gravitational music of the Earth-Moon-Sun system. Some scientists speculate that long-term orbital cycles may influence terrestrial climate patterns, volcanic activity cycles, and even biological rhythms in certain species. Although these connections are still subjects of active research, they suggest that the music of the spheres may be more than metaphor. It may be a real and measurable force that connects all levels of reality, from celestial mechanics to terrestrial biology. The discovery of gravitational waves by the LIGO detector in 2015 added a literal dimension to the music of the spheres. When 2 black holes collide billions of light years away, they create ripples in the very fabric of space-time that travel at the speed of light and can be detected on Earth as minuscule vibrations. These gravitational waves can be converted into audible sound waves, allowing us to literally hear distant cosmic events. The sound of two black holes spiraling toward each other and finally colliding is extraordinary. It begins as a low tone and gradually accelerates and increases in frequency, until ending in a characteristic chirp that marks the moment of collision. It's literally the music of two of the universe's most massive objects, executing their final dance on a millisecond timescale. Let's pause for an extended and contemplative moment to deeply reflect on the extraordinary nature of cosmic time and how our human perception of temporality relates to the vast cycles that govern the movement of celestial bodies. Here on Earth, in our daily lives, we are accustomed to measuring and experiencing time in units that make sense for our biological and social experience. Seconds, minutes, hours, days, weeks, months, years, decades. These human temporal units are derived, ultimately, from astronomical movements themselves: the day from Earth's rotation, the month from lunar phases, the year from Earth's orbit around the Sun. But in the broader cosmos, time unfolds on scales that challenge not only our intuitive understanding, but our very capacity for visualization and conceptualization. Consider that our solar system is approximately 4.6 billion years old. To put this amount of time in perspective, if you could count one number per second without stopping, it would take more than 145 years just to count to 4.6 billion. And this is just the age of the solar system. The observable universe is approximately 13.8 billion years old. During these 4.6 billion years of the solar system's existence, Earth has completed more than 4.6 billion orbits around the Sun. Each of these orbits was slightly different from all the others, influenced by minuscule gravitational perturbations from other planets, by the gradual change in the Sun's mass due to continuous nuclear fusion, by the slow evolution of other planets' orbits, by the gravitational influence of distant stars that passed relatively close to the solar system during their own journeys around the galaxy. But here is something that may leave you genuinely amazed. If you could dramatically accelerate time and watch the entire history of the solar system like a fast-forward movie, you would see that planets not only orbit in repetitive patterns, but also execute much more complex and subtle dances on much larger timescales. Planetary orbits are not static. They evolve slowly. They precesses, which means they rotate slowly like a wobbling top, completing a full precession cycle on timescales of tens of thousands to hundreds of thousands of years. This precession is so slow that it's completely imperceptible on human timescales, but it's real and has important consequences. The precession of Earth's orbit is responsible for the famous Milankovitch cycles, subtle changes in the shape, orientation, and inclination of Earth's orbit that occur on timescales of 20,000 to 100,000 years. These astronomical cycles profoundly influence Earth's climate, causing the ice ages and interglacial periods that have characterized Earth's climate for millions of years. It's extraordinary to realize that the orbital dance that keeps our Earth in habitable position is also responsible for the very long-term climate changes that shaped life's evolution on the planet. Not just the anthropogenic climate changes of recent centuries, but much more dramatic natural changes that occur due to subtle variations in Earth's orbital geometry. Have you ever thought that the orbital dance connects the past to the future in an absolutely fundamental way? The orbital position Earth occupies today is the cumulative result of billions of years of orbital evolution, and the position we will occupy millions of years from now is being determined by the gravitational forces acting on us at this exact moment. There is something profoundly comforting and simultaneously vertiginous in the idea that this dance will continue far beyond our individual lives, far beyond the existence of our species, far beyond the duration of any imaginable human civilization. Long after all human works of art have disintegrated, all human languages have been forgotten, all human cities have become dust. Earth will still be orbiting the Sun, still participating in the same fundamental cosmic symphony. It's a kind of immortality, not our personal or civilizational immortality, but the immortality of the dance of which we are temporarily part. Our individual consciousness is like a brief musical note in a symphony that lasts billions of years. This perspective can be simultaneously humbling and inspiring. Humbling because it reveals our temporal insignificance, inspiring because it reveals our participation in a cosmic harmony that transcends any human scale. What if we could see the distant future with the same clarity with which we see the past? In about 5 billion years, the Sun will begin its final evolution, expanding into a red giant as it exhausts the hydrogen in its core and begins fusing helium in outer layers. This solar expansion will dramatically disturb the orbits of the inner planets. Mercury and Venus will probably be swallowed by the expanded solar atmosphere. Earth may survive physically, but will be transformed into a sterile and scorching world, completely uninhabitable. But even then, even during this dramatic transformation, the outer planets will continue their orbital dances. Jupiter, Saturn, Uranus, and Neptune will continue orbiting what remains of the Sun, eventually a white dwarf. A stellar remnant dense as Earth but retaining most of the Sun's original mass. And these outer planetary orbits may continue stable for trillions of years, much longer than the current age of the entire universe. It's conceivable that even when the last star burns out and the universe enters an era of darkness dominated by black holes, some planets will still be orbiting cold white dwarfs, executing a silent and lonely version of the cosmic dance in almost absolute darkness. There is a poetic melancholy in this vision of the distant future, but also a strange beauty. The dance will continue even when the lights go out, even when there are no more conscious observers to contemplate it. It's as if cosmic music were so fundamental to the structure of reality that it will continue playing even when there is no longer an audience to hear it. But perhaps this is not the only possibility. If life and intelligence manage to persist and evolve for billions of years, perhaps we will find ways to preserve and even orchestrate the cosmic dance. Perhaps we will learn to reignite dead stars, to create new planetary systems, to compose new gravitational symphonies. Perhaps consciousness is the tool through which the universe avoids its own heat death and keeps the music of the spheres playing forever. Now that we have explored the main and most obvious forces that keep planets in orbit, gravity and inertia in their fundamental dynamic equilibrium, let's delve into the more subtle, more delicate, but no less important forces that create fine variations. Minuscule perturbations and long-term evolutions that characterize the true complexity of real planetary movements. Because you see, although gravity is unequivocally the dominant force governing orbital motion, it does not act alone in a vacuum of simplicity. There is an entire orchestra of smaller influences that together create the richness, complexity, and subtle beauty we observe in planetary movements when we study them with sufficient precision and for sufficient time. Imagine that you are trying to balance a coin standing on a perfectly smooth table. Gravity, of course, wants to knock it down, pulling it inexorably downward. But small, almost imperceptible air currents, minuscule vibrations transmitted through the table, even your own breathing or heartbeats can influence whether it remains balanced or finally falls. Planets face similar balancing challenges, but on a much larger scale and with consequences extending over millions and billions of years. One of these subtle but cumulatively important forces is solar radiation pressure. Have you ever felt the comforting warmth of the sun on your face during a sunny spring day? That sensation is not just thermal energy being absorbed by your skin. It's literally billions upon billions of light particles. Photons continuously colliding with your skin in a constant microscopic rain. In the vacuum of space, this solar radiation pressure is constant and omnipresent. For large objects like planets, radiation pressure is completely negligible compared to gravity. But for smaller objects, small asteroids, cosmic dust particles, ice grains in planetary rings, this pressure can be significant over geological timescales. Even more fascinating is the so-called Yarkovsky effect, a phenomenon that sounds almost like science fiction but is absolutely real and measurable. When an asteroid slowly rotates in space, it absorbs solar energy during the asteroidal day and re-emits this energy as infrared radiation during the asteroidal night. But due to rotation, the nighttime side that is emitting thermal energy is not exactly opposite to the daytime side that is absorbing solar energy. This temporal asymmetry between absorption and emission creates a tiny but persistent propulsive force. It's as if the asteroid were a microscopic space engine powered by sunlight itself. The force is so small it would be like trying to push a truck with a gentle breath, But in the vacuum of space and over millions of years, it can significantly change the orbits of small asteroids. Think also about gravitational tides, forces that are subtle but important extensions of basic gravity. Just as the moon causes tides in Earth's oceans, making sea level rise and fall twice a day in a regular cycle, all celestial bodies exert tidal forces on each other. Tidal forces arise because gravity decreases with distance. The side of a planet that is closer to a moon or another planet feels a slightly stronger gravitational attraction than the opposite side. This difference in force, though small, can slightly deform planetary objects and, over time, affect their rotations and orbits. Have you ever wondered why the moon always shows exactly the same face to Earth? Why do we never see the dark side of the moon from Earth? This is the result of tidal locking. Earth's gravitational forces gradually slowed the moon's rotation billions of years ago. Until its rotation period exactly equaled its orbital period around Earth. It's a perfect example of how subtle forces, acting persistently for geological ages, can create profound changes in celestial movements. The moon was not born locked. It evolved to this state through the cumulative action of minuscule tidal forces applied billions of times over billions of years. Tidal forces also heat the interior of planets and moons through internal friction caused by gravitational deformation. Io, Jupiter's volcanic moon, is the most volcanically active object in the solar system precisely because it is subject to extreme tidal forces due to its proximity to Jupiter and orbital resonances with other Jovian moons. And there is an even more subtle and exotic force, gravitational waves. When two massive objects orbit each other, especially when they are very close and moving very rapidly, they create minuscule ripples in the very fabric of space-time that propagate outward at the speed of light. These gravitational waves carry energy away from the orbital system, and this causes the orbiting objects to gradually approach each other in a slow but inexorable spiral. For planets orbiting normal stars, this effect is so small that it's completely negligible even on cosmological timescales. But for extremely massive and compact objects like black holes orbiting each other, the energy loss through gravitational waves can be dramatic. The binary pulsar system PSRB 1913+16, discovered in 1974, provided the first indirect evidence for the existence of gravitational waves. The two neutron stars in this system are spiraling toward each other at exactly the rate predicted by Einstein's general theory of relativity, losing orbital energy through gravitational wave emission. All these subtle forces remind us that the universe is a place of extraordinarily delicate balances and complex interconnections. The stable orbit that seems so solid and reliable to us is actually the result of an incredibly complex dance between dozens of different influences, each contributing its own subtle voice to the cosmic symphony. It's humbling to realize that our existence depends not only on the obvious main forces, but also on all these smaller influences acting in harmony. If any of them were significantly different, if the physical constants governing these forces were slightly altered, the entire delicate balance that allows the existence of habitable planets could collapse. But there is also something profoundly beautiful in the complexity of this interdependence. Each force, no matter how small, plays a role in the grand symphony. Even the most subtle influences contribute to the richness and complexity of planetary motion. It's like a musical composition where each instrument, even the quietest, adds its own unique coloration to the overall harmony. In the last 3 decades, humanity has embarked on one of the most extraordinary and transformative journeys of scientific discovery in the history of our species. The systematic and increasingly successful search for planets orbiting other stars, exotic worlds that execute their own unique versions of the fundamental orbital dance in distant solar systems scattered throughout the galaxy. Each new world discovered reveals a new variation in universal orbital choreography, exponentially expanding our understanding of how diverse, creative, and surprising planetary systems can be. It's as if each discovery opened a new door in an infinite gallery of cosmic art, where each work represents a unique solution to the fundamental problem of how matter and energy can organize themselves into stable systems around stars. Imagine the extraordinary and almost mystical excitement of astronomers when they first detect the subtle signal of a distant planet. They cannot see it directly. Even the largest terrestrial telescopes cannot resolve individual planets orbiting other stars due to the enormous distances involved and the overwhelming brightness of host stars. Instead, most exoplanets are detected indirectly, through the minuscule but measurable effects they cause on their stars. The transit method, one of the most productive exoplanet discovery techniques, detects microscopic decreases in a star's brightness when a planet passes between us and the star, causing a tiny partial eclipse. These brightness decreases are so small, typically a fraction of a percent, that it's like trying to detect a fly flying in front of a powerful headlight kilometers away. The precision required for these detections is truly extraordinary. Instruments must be capable of measuring changes in stellar brightness on the scale of parts per million, maintaining this precision for months or years to detect multiple transits and confirm a planet's existence. It's a testament to human ingenuity and persistence that we have managed to develop technology capable of such delicate measurements. Another fascinating technique is radial velocity, where astronomers measure how a star wobbles slightly due to the gravitational attraction of orbiting planets. When a planet orbits a star, both the planet and star actually orbit around their common center of mass. For a distant observer, this makes the star move in small circles or ellipses in space. This stellar motion is detected through the Doppler effect. When the star moves toward us, its light is slightly shifted toward blue. When it moves away from us, it's shifted toward red. The velocities involved are minuscule, sometimes just a few meters per second, equivalent to the speed of a casual human walk. It's incredible that we can detect such subtle movements in objects tens of light years away. Each exoplanet discovery reveals how creative and diverse the universe can be in creating planetary systems. There are planets that orbit two stars simultaneously, worlds where one day lasts longer than 1 year, giant gas planets that orbit their stars closer than Mercury orbits the Sun, and rocky worlds in orbits so eccentric they experience more extreme temperature variations than any environment in the solar system. One of the most fascinating and scientifically important systems discovered is Kepler-16b, affectionately nicknamed Tetuvin in honor of the fictional Star Wars planet that orbits two stars. This world really exists and really orbits a binary star system, confirming that such configurations are not only possible but apparently common in the universe. Imagine for a moment what it would be like to grow up on a world like Kepler-16b. The sky would present visual spectacles that have no parallel in terrestrial experience. Sometimes both stars would be simultaneously visible during the day, creating two sets of shadows for each object and producing complex and ever-changing illumination. During certain epochs of the planetary year, one star would set while the other remained high in the sky, creating periods of perpetual twilight with colors and light intensities impossible to replicate on Earth. How would hypothetical civilizations that evolved on such worlds develop their concepts of time? How would they create calendars to track their complex seasons? How would they measure days and nights when terrestrial concepts of sunrise and sunset would be completely inadequate? Perhaps they would develop completely different temporal systems, adapted to the unique rhythms of their particular cosmic dance. And then there are the fascinating hot Jupiter's giant gas planets that orbit their stars in a matter of days, or even hours, much closer to their stars than any planet in our solar system. These worlds completely challenge our original theories of planetary formation, because gas planets shouldn't be able to form so close to their stars, where intense stellar radiation would prevent the accumulation of ice and volatile compounds necessary to form massive planetary cores. The discovery of hot Jupiters forced astronomers to fundamentally rethink how planetary systems form and evolve. We now know that planets can migrate dramatically from their original formation positions, spiraling inward through interactions with the gas and dust disk from which they formed, or being hurled into new orbits through violent gravitational encounters with other planets. The discovery that planets can migrate dramatically changed their orbits over time, revolutionized our understanding of planetary system evolution. It's like discovering that dancers in a choreography can change their positions on stage during the performance, creating new patterns and dynamic arrangements over time. This forces us to question fundamental assumptions about our own solar system. Has it always been as it is today? Growing evidence suggests not. Jupiter and Saturn probably migrated significantly during the first millions of years after solar system formation. And this migration may have been crucial to establishing the stable orbits we observe today. Some models suggest that Jupiter initially migrated inward toward the Sun, perhaps coming as close as Mars's current orbit, before reversing its migration and moving outward to its current position. This epic journey of Jupiter, called the Grand Tack by astronomers, may have swept primitive rocky planets into the Sun and completely redistributed the architecture of the early solar system. It's humbling and simultaneously exciting to realize that even our normal planetary configuration is the result of a complex and dynamic history of changes, migrations and adjustments that extended over millions of years during the solar system's turbulent youth. Our Earth may have arrived at its current orbit through a much more complex and dramatic process than we ever imagined. We now arrive at a deeper and philosophically richer contemplation about what it means to exist as conscious beings in a universe where everything is in constant motion and perpetual transformation, but where certain dances and patterns persist for eras that transcend any biologically relevant timescale. There is a fascinating and profoundly revealing philosophical tension between the apparent permanence of planetary orbits and the fundamental and incessant change that governs the entire observable cosmos. On one hand, when we look at the night sky with our limited but wonderful human eyes, we see apparent permanence and comforting stability. The constellations appear fixed and immutable, eternal in their familiar configurations. Planets follow predictable paths with chronometric precision. Seasons repeat faithfully year after year with a regularity that our civilizations have used for millennia to organize agriculture, navigate the oceans, and mark time. This celestial regularity gave ancient humans a deep sense of cosmic order, a comforting sensation that there were reliable and predictable patterns in a world often chaotic, unpredictable, and threatening. Stars were seen as eternal reference points, navigational guides that could be trusted through generations. Planetary cycles provided natural calendars for planning plantings and harvests. On the other hand, we now know through modern science that this apparent permanence is, to a large extent, a perceptual illusion created by the brevity of our individual lives compared to astronomical timescales. Everything in the universe is changing, evolving, transforming, only on timescales that challenge our perception and direct experience. The very stars of familiar constellations are moving through the galaxy at velocities of tens of kilometers per second. In a few 100,000 years, a blink of an eye in cosmic terms, the constellations will have changed dramatically in shape. Planetary orbits are slowly evolving through complex gravitational perturbations. The solar system itself is traveling on an epic journey around the galactic center that will take hundreds of millions of years to complete. Have you ever wondered deeply which perspective is more true or fundamental? The permanence we perceive directly with our senses, or the change that science reveals through instruments and theories? Perhaps this is a malformed question. Perhaps both perspectives are equally true and valid in their own appropriate temporal and spatial scales. For us, with our lives of decades and our limited sensory experience, planetary orbits are gloriously stable, reliable, and predictable. We can plan our lives around the seasons, we can program eclipses centuries in advance, we can send spacecraft to encounter distant planets at specific moments calculated with extraordinary mathematical precision. For the cosmos, with its perspective of billions of years and its scale of light years, everything is in constant flux, perpetual change, continuous evolution. Stars are born and die, galaxies collide and merge, the universe itself expands and perhaps one day will contract again. There is a profound and almost mystical beauty in this duality of perspectives. It teaches us something fundamental about the nature of reality, that stability and change are not irreconcilable opposites, but complementary and interdependent aspects of existence. Planetary orbits are stable precisely because they can adjust, adapt, and gradually evolve over time. If orbits were truly rigid and completely immutable, any perturbation, a passing asteroid, gravitational influence from a distant star, a change in solar mass would destroy them catastrophically. It's precisely their capacity for subtle change and gradual adaptation that allows them to persist for billions of years. This leads us to a profound reflection on our own existence as conscious living beings. We too are part of this fundamental cosmic dance, subject to the same physical laws that govern planetary movement. Our stability as living organisms depends crucially on our continuous capacity for change and adaptation. Our cells constantly renew themselves, our thoughts evolve day by day. Our personalities develop and transform throughout our lives. And just as planets find stability through constant orbital motion, perhaps we find meaning and purpose through change, growth, continuous exploration. Perhaps the universal human quest for learning, personal growth, exploration, and discovery is our unique version of the orbital dance, a movement that keeps us in dynamic equilibrium between destructive stagnation and disintegrating chaos. There is also a deep ethical and moral dimension to this cosmic contemplation. If we are an integral part of the cosmic dance, if we are subject to the same fundamental laws that govern stars and galaxies, then perhaps we have a cosmic responsibility to dance with grace, harmony, and beauty, to find our own personal balance between the forces that pull us in different directions, to contribute constructively to universal harmony instead of disrupting it through our actions. What if our consciousness, our unique capacity to contemplate and understand these cosmic laws, is our special and irreplaceable contribution to the universal symphony? What if we are the instruments through which the universe becomes conscious of its own mathematical beauty, its own physical elegance, its own capacity to create order, complexity, and meaning? This perspective completely transforms our understanding of our place in the cosmos. Instead of being external observers trying to understand an alien universe, we are internal participants in a cosmic process of self-consciousness and self-understanding. We are the universe trying to understand itself through the limited but precious lens of human consciousness. We finally arrive at the concluding chapter of our contemplative journey, but like every truly satisfying conclusion, it should open new questions and possibilities instead of definitively closing them. Let's now turn to the future, both near and unimaginably distant, of the orbital dance that sustains our cosmos, and that has been the focus of our deep contemplation. In the near and tangible future, humanity is actively preparing to become a genuinely multiplanetary species. We are planning to return to the moon with permanent missions, send the first humans to Mars to establish self-sustaining colonies, and perhaps one day even send brave explorers to other star systems to directly study worlds orbiting distant stars. When this happens, and evidence suggests it will happen within this century, we will become direct participants and personal experimenters in the orbital dance of other worlds. We will personally experience what it's like to live under different gravitational intensities, orbit different stars, experience different durations of days and nights, observe different configurations of moons and planets in the sky. Imagine what it will be like to wake up on a Martian morning and see two small irregular moons in the sky, Phobos and Deimos, moving at visibly different speeds due to their peculiar and close orbits. Phobos, the closer moon, rises in the west and sets in the east, completing more than 3 orbits per Martian day. Deimos moves more slowly, taking just over 1 Martian day to cross the sky from east to west. Or imagine being on a permanent lunar base, where Earth always remains at the same point in the sky, passing through its majestic phases from new Earth to full Earth in a cycle lasting an entire lunar month. Imagine watching Earth slowly rotate, seeing continents and oceans pass by in a hypnotic rotation lasting 24 Earth hours. But the distant future reserves even more dramatic and fundamental transformations for us. In approximately 4 to 5 billion years, our star, the Sun, will begin its final stellar evolution. As it exhausts the hydrogen in its core and begins fusing helium in outer layers, it will expand dramatically, becoming a red giant hundreds of times larger than its current size. This solar expansion will profoundly disturb the orbital dance that has remained stable for billions of years. Mercury and Venus will probably be completely swallowed by the expanded solar atmosphere, their orbits ending in a final spiral toward the center of the giant star. Earth may survive physically, but will be transformed into a completely sterile and uninhabitable world, with its atmosphere and oceans vaporized by the intense heat. But even during this dramatic transformation, the outer planets Jupiter, Saturn, Uranus, Neptune will continue their majestic orbital dances around what remains of the Sun, eventually a white dwarf, an extraordinarily dense stellar remnant about Earth size but retaining most of the Sun's original mass. And these outer planetary orbits may continue stable for trillions of years, much longer than the current age of the entire observable universe. It's a simultaneously melancholic and sublime prospect. Even when our star dies and our home planet becomes uninhabitable, the fundamental cosmic dance will continue on a timescale that defies any intuitive human understanding. Even further in the cosmic future, when the last stars burn out and the universe enters an era of darkness dominated by black holes and cold white dwarfs, some planets may still be orbiting these stellar remnants, executing a silent, solitary, and invisible version of the cosmic dance in almost absolute darkness. There is a deep poetic melancholy in this vision of the distant cosmological future, but also a strange and transcendent beauty. The dance will continue even when the lights go out, even when there are no more conscious observers to contemplate and appreciate it. It's as if cosmic music were so fundamental to the very structure of physical reality that it will continue playing eternally, even when there is no longer an audience to hear it. But perhaps this melancholic vision is not the only possibility or the only possible destiny. If life and intelligence manage to persist, adapt, and evolve for billions of years, a prospect that is speculative but not impossible, perhaps we will find technological ways to preserve, prolong, and even actively orchestrate the cosmic dance. Perhaps future civilizations will learn to reignite dying stars, build artificial stars, create custom-made new planetary systems, compose new gravitational symphonies with precision and beauty that transcends any natural work of art. Perhaps consciousness and intelligence are the tools through which the universe can avoid its own heat death and keep the music of the spheres playing forever. Have you ever thought that by contemplating these profound questions about the cosmic future, you are participating in something absolutely extraordinary and privileged? You are stellar matter that evolved to become conscious, capable of understanding the laws that govern your own physical existence. You are literally the universe contemplating itself, trying to understand its own past, present, and future destiny. And this brings us back in a circular and satisfying way to the beginning of our contemplative journey. Do you remember when I asked where you were, what time it was, how you felt at the beginning of this narrative? Now, at the end of this extensive contemplation, you are still in the same physical place. But I deeply hope you are in a different place mentally, emotionally, and spiritually. I hope you feel a deeper, more visceral, and more meaningful connection with the cosmic dance of which you are part at every moment of your existence. I hope you have developed a richer appreciation for the mathematical elegance that governs planetary motion. I hope you have gained a broader perspective on the scales of time and space in which our existence unfolds. Because you see, even when this narrative ends and you return to your normal daily activities, the cosmic dance will continue inexorably. Earth will continue its faithful orbit around the Sun, carrying you with it at 30 kilometers per second through the vacuum of interstellar space. The solar system will continue its epic journey around the galactic center, and you will continue being an active and conscious participant in this extraordinarily magnificent cosmic symphony. Perhaps, the next time you look at the starry night sky, you will remember this contemplative conversation we shared. Perhaps you will physically feel the dizzying speed with which you are traveling through space as a passenger on the spacecraft Earth. Perhaps you will realize with new clarity that you are not just passively observing the cosmos, you are the cosmos, actively participating in its own contemplation and self-understanding. I sincerely thank you for accompanying me on this intellectual and spiritual journey through the invisible forces that keep our world in harmonious motion. I thank you for lending your imagination, your curiosity, your innate capacity to marvel at the beauty and complexity of the universe. In a vast, ancient, and often seemingly incomprehensible cosmos, moments like this, when consciousness directly encounters cosmic grandeur, are precious beyond any material measure. And now, as we prepare to formally conclude this contemplation, I leave you with a final question to carry with you and meditate on in the days to come. What if One day, that delicate and apparently eternal balance that keeps planets in their stable orbits were suddenly or gradually broken. What if we discovered that the cosmic dance, however eternal and immutable it seems to our limited perception, is actually more fragile, more contingent, and more dependent on specific conditions than we ever imagined? How would this realization fundamentally change our perspective on our responsibility as conscious and unique participants in this extraordinary universal symphony?